Welcome to my presentation. Thank you for introduction, Ivan. And yes, so today we heard quite a lot about the technology already, about the platforms dedicated for it and the product. But by now we didn't hear anything about the main part, which is connecting all of them, so about the design. And within my presentation, I will teach here a bit more on the perspective of how we can go through the platform to the design, and mainly how to account for this integration part, in interfacing part between different platforms within the single design, within the single final chip we want to get. So very briefly about the company. So VPIphotonics is a software company uh, providing the software solution for simulation, optimization, and design of optical circuits. And not only, but to this I will come in a second. We are also offering some services, some design services. So we are on the market over 25 years already with regional offices in Europe and North America, with a lot of the global networking resellers all over the world. We are mainly facing with the three eyes. So firstly, integrate. So we try to really integrate all the simulation techniques, starting from the devices to the systems, enabling you the design not only from the perspective of the cross section through the photonic circuit, but also from the system perspective. So mainly how your PIC should behave in the whole system, where you will connect it with multiple other components like fibers or DSP afterwards. The second eye is the interoperable. So we are trying mainly to make the interface with many different third-party simulation tools to not limit only you to the functionality of the program itself, but also to allow you mainly to interface with all other tools, for example, for electronic simulation, for layouting, and much more, which I will also mention in some examples directly. And the third industry leading, so we are cooperating with many industrial and research collaborations to develop state-of-the-art PICs, also to set some standardization. And I will just show you few examples which are touching directly the problem of the hybrid integration here. So from our product perspective, I mentioned we are covering everything from the device to the system level. Today, I will focus only on the PDK interface, which are allowing us mainly to link the Foundry dedicated components to enable the PIC design with them and fabrication of the chip afterwards. So very shortly about the PDK, in a standard approach, the Foundry just provides some kind of the description of their processes in the form of some PDK library describing all necessary information, including the performance of the building blocks, layouts of them, but also the detailed description of the process that is created, that mainly reflects the technology steps in order to fabricate it. Based on this, there are some PDK compact model database created, and we are created simulation models for it. These models mainly take the information from either measurement of the fab or simulations. And of course, you want to bring this in hopefully some standardized format that will enable automatic creation of this generated simulation modules. Then once you are having the simulation models, you are of course building your circuit design, which you are interested in. And here I will come back to this example, but we see the reproduction of the widely tunable laser, which was shown by Moritz in HHI. But yeah, as I mentioned, I will come back to this. The idea is that mainly we can simulate the PIC itself, but we can also verify this PIC on the system level. We can co-simulate it with the electronics. And once we are happy with the design, we can extract the layout process with the layout design in order to prepare the GDS file, send it to the fab to get our assembled PIC. So now I will talk briefly about the different approaches which are used between different platforms in order to enable this hybrid PIC design. And first, I will start exactly with mentioning of this of this transceiver in that part, which is a bit extended version of the HHI laser shown before. But mainly, yes, we are interested in the final design, which you can see is already including some fiber component, including the coupled laser with the photodiodes on chip. But we start just with the building blocks. So how we do it, how we go through it. Yes, maybe one more thing to mention. You can see that within the PDK library for this polymer platform, we are already having some indium phosphide components. And that's exactly one of the typical approaches how foundries can enable directly integration of the platforms. So you are just building your polymer chip, which will include directly on top of it some additional gain sources, some additional photodiodes, or modules which are enabling direct coupling to the fibers. And based on those components, they are already optimized for the fab, and they can be fabricated and assembled by the fab directly. This means that after your simulation, after you can show the results which you are expecting, you can directly export the layout to one of the desired layout tools and process with the with the GDS generation. Please note that the GDS is including only the layers here which are belonging to the polymer chip, but you can see there are some predefined spaces which are enabling you directly the integration of these components with this different platform modules. And in that case, if you provide such design with additional information how this needs to be coupled, HHI the assembly everything and provide the final chip, which is assembled here within the polymer chip fabricated by them, and also the indium phosphide components created by their foundry of generating the structures indium phosphide. Okay, but what's happening to all other foundries which they don't really include the information about the standard component integration? So standard designs for the silicon nitride, lithium niobate, or polymers, they don't really have directly the modules which are being enabled there by the fab. And in that case, there are mainly two approaches by now, how you can make a design and fabrication. Firstly is directly talk to the fab and discuss with the fab what kind of building blocks they are offering. And here a good example was the design which I mentioned already before, although the building blocks were generated there in the PDK directly, but you can discuss about different kind of indium phosphide lasers or gain chips, which could be coupled there directly. On the other side, you can also use some external light sources. And here, there is another case, so you can find out many pluggable or bar chip lasers for visible light, a lot of QCL laser for mid-infrared, but there is one big issue with them. So there is no clear information how to build interface with them unless provided by the fab or provided by the laser manufacturer. So here we see some different laser sources which we generated between different projects with some structures for visible and short near infrared for C-band and also for the mid infrared. They all were optimized in that case based on the project work for given platform. If only you would like to use these components with some other platform, of course, this means that you need to build your own interface module. And let's show this how we can do it on the example. But first, how we could generate, in that case, a platform, a template of the PDK that could work for us directly by enabling generation of your own custom PDK. So here we have a process of generating such custom PDK. Mainly, it will include some templates. It will include some additional layout information. And while you are creating your own PDK, you can easily protect the IP. You can extend the PDKs, the existing PDKs, and share them mainly with your own interest partners. And if you are interested in this process, please refer to the paper that we recently, the article that we published at the start of the year about mainly design freedom and IP protection using the PDK. And how this PDK can be used based on the example, I will show here the hybrid integration of the mode-lock laser using, on the left side here, we can see the silicon nitride extended cavity based on the Lionics. And here we have the the SOA structure 3.5 based on the smart photonics. And this idea was mainly recently published, or recently 3 years ago published by the Visors, mainly explaining on the design itself and fabrication of the structure. So very easily we are creating a library of the components. We are using in that case on the left side the components for the silicon nitride equivalent with the PDK of Lionics. On the right side we have the indium phosphide components equivalent to the smart photonics and adapted to the performance of the measured devices. And here we see one additional magic component, which is actually the spot sign converter between one and the other platform. I'm especially not looking into this component, but if you are interested exactly how it functions and what can be done here, you can refer back to the paper. It's described in details, including even some tolerances of the coupling and misalignment with the total map, how the coupling should behave. But for the perspective of the design, I would like to refer more that, of course, such combined platforms, we have some design with the combined with different platforms can be created on a single chip when you are directly simulating the performance. So here we can see our spectrum of our laser, we can measure the repetition rate and also observe the waveform very similarly to the ones which were achieved in the paper. And of course, what we can do on top of it, we can perform some tolerance analysis, either based on the implemented by the Foundry tolerance analysis or by just varying of the interest and providing given tolerance analysis of our choice. In that case, I was using mainly the provided information from smart photonics on the tolerances plus some additional Gaussian variations on given components to investigate mainly how the frequency shift of the main peak, so the peak power of the whole spectrum, and also the maximum power of the spectrum will behave based on given number of runs. So to conclude with the standard approach, which was very often shown, what you can do for us. Firstly, of course, you can use our tool to develop your own PDKs and share them with your customers in order to allow them to really follow up with your designs. But also we will be very happy to get feedback from you regarding your design needs and regarding your PDK development, especially if something you believe should be added on top of the tool. And where we can help you, mainly we are helping here with enabling the various strategies for the peak design, offering the workflow from devices to the systems via, of course, circuits, and by offering you the custom PDK framework, enabling you mainly to develop your own components and interfaces to build the design and be able mainly to fabricate those integrated platforms directly. Just maybe short comment only on at the end, we are helping to accelerate this design together with the export to the layout, which we presented already several times before. And also we are offering the personalized support with the help to develop this PDKs. So if only you have some interest in those topics or many others, which I just listed, feel free to contact us either directly or via Ivan or at ECOG, we are also there. So if you have any questions, please feel free to contact us, and I'm also happy to answer now if we still have time.
Thank you.